All right, so welcome to our panel. It's your opportunity to ask us questions, get to pick the brain of these wonderful people here. So actually, because we had a few talks which didn't have the chance to have questions, I'll start if anybody has a question that they're dying to ask. Don't be shy. Yeah.
Please send the mic in the...
Hello.
Can you stand, please?
Oh, of course. Hello. I have a question for Professor Bengio. During your talk, you mentioned that causality is a very important aspect of how humans recognize the world and understand how it works. But causality is also a very slippery concept. So, for example, when I push a door open, it opens because I wanted it to open, but it also opened because there was nothing behind it stopping it from being opened. And it also opened because of the laws of physics. So how exactly would you embed this very slippery concept into any kind of reasoning system? Because to the best of my knowledge, even philosophers have a very hard time defining what causality even is.
That's precisely why we need computer scientists. Sorry. So first of all, in your example, there are multiple causes, but that's fine. We can have a whole graph of causal dependencies. Maybe the more interesting question is, how do we figure out what are the right causal variables? This is a question that causality researchers haven't really addressed up to now. So first of all, there's like decades of work on causality in statistics and social sciences and medicine. I mean, it's a very rich field. It's not as fuzzy as you seem to think. I encourage you to read, for example, the work of Julia Pearl, or the book that I mentioned in my presentation by Shopkoff and collaborators. In machine learning, it's a fairly new kind of investigation, but I think it's very important that machine learners start really focusing on both the ability to do inference, which is what has been done in most of the work in statistics, but also discovering the causal structure, and in fact even discovering what the variables that we should be operating on should be when you consider like a robot that observes sensory data and has to figure out high-level abstractions. So the way I think to answer this is, I think of causality not as that there is some underlying true causal thing, but more as a cognitive tool that helps reasoning. Right? So we invent abstractions that are convenient because they're good approximations of what is going on out there to help us figure out what would be the impact of our actions. So this is the way I think about causality.
Is there any other question? We have somebody on the right over there.
I have a question for Professor Deng. What would be the optimal way to deal with an inconclusive conjecture, and how would you train that behavior?
Well, you have to give up at some point, like humans do. So in fact, you know, it's known that there are things that are not provable, right? So, you know, it can be impossible to know if a conjecture is true or not. So, you know, what humans do now is keep them as conjectures.
So, when after trying to prove that, there should be a gap between the conjecture and the proof. So would you provide the questioner with that gap, and what more knowledge is required to prove that conjecture, or would you just say that it's inconclusive and not provable?
So right now, basically, the system has a limited time, right? And it will just fail when its time runs out. So certainly, I think it would be good if the system can somehow say, well, okay, this conjecture is too hard. Maybe after I relaxed it and it becomes provable. But we certainly don't have that capability. But it would be something nice to do.
Thank you.
Any other question? In the back over there?
It's a question for Professor Fiedler. So all the simulators, the great simulators that you've shown us today, they are mostly in the visual domain where any human being can be intimately get themselves associate with. So what do you think it will take to expand that notion of the generating some data or AI generating data for the AI in other domain, not only the visual domain, but other domain that we may not be able to intimately familiar with?
Well, I think simulation is beyond vision, right? Like people in physics or climate, weather, they've been using simulations for a long time. So it's more new in vision to actually use these simulations, or for robotics. But even for social networks, or you can do simulations in various different fields. I don't know whether you have one particular in mind.
Well, things like to build a simulator itself, you need some expert knowledge. To begin with, and to get some training data for the AI to generate those simulated environments.
Yeah, that's right. So
in terms of the economics of the human labors, so will it be more difficult to generate those type of things in your opinion?
I mean, here we use artists, because artists, can create beautiful things. In physics, you have people with PhD that have, all the physics equations that can write these simulators. So you always need to have some expert knowledge, right? I think we discussed before, for medical simulations, you also probably need some doctors in the loop that can tell you how these operations could be simulated as well. So I think, to create something that's going to be used as a ground truth later for something, you need some sort of expert domain knowledge. Yeah, it's going to be very hard to just crowdsource something like that.
Somebody in the front here? Youngs, I want this one.
I have a question for Professor Sander Fiedler. I was at the ICCB last week, and some professors talked about this, where creating virtual environment is almost impossible for autonomous driving. And then so they, more like they are arguing about that we have to create more bigger data with annotations. And I think you have researched on both topics, like creating a data set with annotation, and also creating virtual environment for the self-driving. Which is more feasible for you, or which is more sounds convincing?
Self-convincing. I'm convinced on both, man. I think it needs to be some sort of a back and forth. It shouldn't be so segregated, right? Because, like I said, simulation can be used to train AI, and AI can be used to train better simulation. And you need real-world data to inform simulators. And I think why it's so hard for autonomous driving is, in the end, it's really about those difficult situations that is very hard to imagine, like the edge cases that make your systems fail. And you can only do that by driving around, correcting millions of miles and collecting those. And I think that's the hard part, right? But maybe there's a way to kind of imagine those very weird cases, right? We know that we are all restricted with physics, and that's almost the only restriction. So maybe there's a way to kind of mine those scenarios without even seeing them.
Or create some adversarial scenarios.
That's right. And we're working on that.
So perhaps then the one in the back.
Hi, I have a question to the Professor Benju, or the all panels. Actually, over the half a century, we have approached the machine learning by the mathematical ways, like attention algorithms or transformer algorithms. But actually, our brains are works by just the topologies and just like a kind of the spikings. So, could we generate the similar types of algorithms by spiking neurons or and kind of else by biologically?
Well, I mean, there are equations that govern your brain too. So the real question is whether we have more to learn about the brain, which we haven't yet exploited as inspiration for machine learning. And clearly, I believe so, yeah. Now, whether a particular feature like spiking turns out to be important at the information processing level, it's not clear. Some people think so. Some people think it might just be a trick to save energy. And we're doing things like spiking in neural nets that have low precision, for example, with quantizing the activations and the weights. The stuff I presented today is looking for inspiration from cognitive science and cognitive neuroscience. So I think we have a lot more to learn. It has nothing to do whether there's math or no math. There's math everywhere.
Yeah, that's
but it's more whether we can discover principles that work in machine learning settings and also correspond to something used in biology.
Thank you very much.
Hello. I have two questions for Professor Jiang. Yeah. I remember at the beginning of the presentation, there were three pictures. One people riding bicycle and stand aside bicycle and a fixed bicycle, something like that. And your work can generate the captions for last two pictures, even you don't have the data for last two picture. And the second question is, you mentioned knowledge base and with common sense. So is the knowledge base the common sense, or if the common sense isn't knowledge base, so how do you define the common sense?
Okay. So let me try to answer the first question. So we have done some work on scene graph generation that's recognizing objects and their relations together. I don't think our method actually addresses the problem of the model overfitting to language biases. I think to really address the problem, we really need to have better visual representations that go beyond 2D patches. So that's actually the 3D vision work that's trying to address that. Although 3D vision is actually very, very difficult. So I don't think we are at the level where it can substantially help recognition tasks. Okay, so to answer the question is not yet. The second question is the sort of the representation of common sense knowledge. So I think likely it's gonna need to be some kind of hybrid representation. You have a lot of your common sense knowledge comes from visual experience, and also some also come from, let's say, reading books. Okay, so it could be a form of symbolic representation, but no, this is still a very open question.
Okay, thank you.
Any other question from the audience? There's one over there. And if you have a question over there, just wave hi because you're farther.
Can I just sit? Yeah. Thank you for today's lecture. I couldn't see all of lecture, but last two lecture was really great, especially Professor Deng and any other panel. I'm very interested in the symbolic reasoning. The one thing, I could be biased for electronics or signal processing in my background, but for a long time I feel like a neural network is a kind of half of the intelligence in the, let's say, analogy ALU in arithmetic side, like addition, deletion, or some signal strength side, like modeling our muscle. But Professor Deng tried some symbolic reasoning, like a predicate into a high-dimensional embedding, and try to use some deep learning approach that feels very strange for me. So could you explain?
I don't think it's all that strange, because if you think, let's say, some of the mathematics actually about geometry, in those cases you actually do want to build geometric intuitions, and certain things would be obvious. Like if I say, you're facing a building, now you turn right, where is the building relative to you? So you can treat it as a symbolic way, but actually mapping it to a continuous representation, a spatial representation, would make it a lot easier. So that's one of the reasons. And also, when we are manipulating symbols, we do observe patterns and similarities. We might have ideas about certain results, previous results, or certain theorems might apply in the situation because we observe some kind of similarity of structures. Now, the idea of similarity is, it can be very well modeled by vector representations. So yeah, that's sort of that's my intuition about why using it would be a good idea to use deep learning for symbolic reasoning.
So maybe I could add something here connected to my presentation this morning. The way humans do logic is not by brute force search, because of the exponential explosion of number of possible trajectories that you might need to look at. Instead, we use very strong intuition that does most of the work to suggest which trajectories to look at. In fact, we do even better than that. We don't even need to go full trajectories. In fact, humans have a very hard time to make correct proofs. They do sort of proof sketches. We're very good at proof sketches. And often rather use machines to fill in the details, or grad students. No, because it takes a lot of patience, and human brains are not good at that, at looking at the details carefully. But we're very, very good at having the intuition about what is a good direction to explore. And I think in order to do theorem proving, reasoning, logic the human way, we need to combine some of the aspects of logic, of combining small pieces of knowledge in a rational way, along with the system one intuitive approaches that have been very successful for deep learning in the last few years.
So about proof, I think I'd like to mention that you were doing a bit of projection, Joshua, because you're very intuitive. But I've had two types of students. So there are the students who are more intuitive, they make big jumps, sometimes have a bit more trouble fitting the details, whereas there are some others which are much more automatic in some sense, like more making small steps. Yeah, and for them, they have this very detailed approach, and it will get somewhere.
Yeah, but you can't get very far this way.
That's true. Yeah, I'm saying there's still some humans who do that.
Yeah, that's right.
Oh, Young-sang.
I have a question to Dr. Chang and then Dr. Cho, both, because in dealing with that very long text in generation of understanding, like in summarization and translation, I think there need to be a hierarchy of abstraction to deal with very long text. So what is your idea on how can we deal with effectively with the abstract hierarchy in natural language?
Yeah, that's a great question. So I think what we've explored classically in NLP is to have a theory of what the hierarchy should look like and impose that and then try to learn it and then do processing based on it. And I think what we've learned now with deep learning is that maybe it's too easy to go wrong. You've discretized too soon in that way. So I think what we should do is we should still be inspired by those theories, but try to learn this hierarchy maybe more implicitly, maybe have some priors for sparsity or something like that to try to encourage this structure to be discovered in a way that is appropriate for whatever task you're solving.
Yeah, I mean, well, it's difficult to say otherwise to what Jackie said. But I think the more interesting question here is that whether that kind of hierarchy needs to be informed externally or whether that hierarchy actually emerges automatically from observing and learning to generate long documents automatically. So there was always the question about not even a long document, but even a sentence when I was presenting earlier, let's say a few years back, like how to show them how the LSTMs can generate sentences in a coherent way. There was always a question about how that LSTM can do that when it does not have any idea about the different scales of time in generation or the way to memorize or plan out. But it turned out what was happening is that these LSTMs were in fact building up the plan on its own in a continuous, let's say, way. And then to build the hierarchy also within that high dimensional space they was learning to capture. So in that sense, what I think, well, what I prefer is that our models with the minimal amount of the knowledge about the hierarchy injected are anyway going to capture this very complicated hierarchy from observing data automatically. And then in machine translation, let's say when we look at the WMT, this year's WMT challenge, what we see is that the very same model that we've been using for sentences that were trained now on the document level are indeed working better than the sentence level translation. And then just looking at that, it's pretty much a good guess that there is some kind of hierarchy that have been automatically captured about the document within the gigantic transformer that has been trained.
So I also have questions for both of you, Kyung-Young and Jackie. I was wondering if the kind of method, the second method you talked about with the latent variables, might be applied to abstractive summarization, because it feels like it has a lot of the features of the way human would do it, of iterative refinement based on some latent sort of abstract summary in a continuous vector domain. So what do you guys think?
Yeah, I think that would be a really good direction to explore. I think what needs to go with that is you need kind of the right task set up for it. So I think that, for example, a lot of the abstractive summarization I'm interested in right now is where it's not about paraphrasing, it's really about abstracting multiple events into one single description that covers both of them, or all three or four of them. And I don't think that'll just emerge that easily. I think
well, that goes back to the hierarchy problem, right?
Right. But I think at this level, you'll still need some training data and the right task setup and the right formulation of the input and outputs, along with something like a latent variable model.
You don't trust unsupervised learning? Or
not enough for now.
Rather weak labels?
I think it'd be great if that works, but I think at this point we still need to give it more push in the right direction.
So in my case, I have a full trust in unsupervised learning. But what I think is really interesting with these latent variable models is that these are really somehow allowing us to solve this very high-dimensional combinatorial optimization problem, which, as Joshua said, if we wanted to solve in a brute force manner, it's just absolutely impossible for us to do anything about it.
So you can go from like the search-based solutions to something that's more greedy, essentially, right?
Yes, precisely. And then even though it's greedy, but we can now have much more power within this continuous latent space for us to actually explore this space much more efficiently with much more information that has been extracted out of the large amount of data we have. So in a sense, it's really interesting way to lift the problem of combinatorial optimization into the continuous, let's say, convex optimization problem. And that's how I view it. And then I believe that's the only way these problems can be solved. And then that's probably how we solve it as well, in some sense. And then I think the unsupervised learning is going to actually get us there at some point. Yes.
In the middle?
Hello, and thank you for a very inspiring talk for you guys. I have two questions for Simon and just simple one question for Jackie Chan. And just one question about Simon. Is it? Yes. Okay. And my question is that, did you do some experiment about of some more bigger pictures, much bigger than CIFAR10? And the extra gradient method is necessary for your work?
Okay, so the question about size, no, we had a bit of a computational issues. So in particular, I would like just to say a few words about this, because what happens with these methods is that you download the code from some authors, you run it, and it kind of works. But if you change anything, it stops working. And then, for example, meaning by changing anything, you change the architecture, or you change the optimization algorithm, this kind of stuff. Then you need to do hyperparameter search. And that's what's extremely expensive. And that's why they use these big cluster. And actually, in our first iClear paper, one of the students was at FAIR, and I didn't realize it until in the next paper, I didn't have any Facebook student. And then we realized that, okay, it takes forever to do these search. So we didn't do big images, in particular because of that. The other thing is also when you go to deeper architecture, that's when you get this interesting behavior where everything starts to diverge. Like you to get good results, you have to be at this edge of convergence, and then at some point it starts diverging. Now, whether extra gradient is necessary, I don't think so. Like we could also, we also did experiments with just variance reduction plus the gradient method, which somewhat works. On MNIST, everything works. I think on more complicated data set, we did more experiments with extra gradient. We felt it was a bit more stable. I think in the convex world, there's a big difference between them. In the non-convex world, there's a lot of other factors. So I think it will be, this is just, these are new methods in some sense that has not been applied to this before, like 2 years ago. So I think there's a lot of empirical work to do to get more conclusions.
Thank you. And
sorry, from a theoretical perspective, though, I find extra gradient much better motivated, and actually it will converge in cases where the other method won't converge. So I think that's quite compelling too, as a good method.
Okay, thank you. And question for the Jackie Chan is, I have read a novel called Sound and Fury, and when I read that novel, I can't tell who is the important person. So when you do summarizing synapse, how can the model tell which one is very important person? Because like Harry Potter, Cedric's death is very important, but just few part of the series. The fourth series of Harry Potter is like 4 books, and just like 1-2 paragraphs is about the Cedric's death, right? But that part is very important for the novel. So yeah.
Yeah, so this is a choice you have to make when you're processing the story, right? So for us, we took the protagonist. So there are definitely other important characters in these stories, which we are not currently trying to generate attributes for. So instead, we took the protagonist, which is really they are mentioned the most in the story. So it's possible that this works especially well for short fiction that might be relatively simple compared to maybe some other kinds of novels. But so that's the assumption we took with this data set.
Okay, thank you.
So just for the context, we have about 10 minutes left. So if you have a question you really want to ask, like, you will have to raise your hand. So I think I will go over there, and then I will go back to you in the front.
Hello, I have a question to Professor Jackie. So when you summarize fictions, I was interested for how you define some features that composes a synopsis. And actually, I want to know that kind of feature engineering could be automized. As future learning in image task can learn to learn some certain shape or edges from images, do you think it would be possible to make machines learn to identify certain set of characteristics from small set of documents? And if so, what kinds of features could be learned from that?
Yeah, so in our work, it was really to establish a baseline for this problem of generating character attributes. So I think the main contribution of that paper and that work is to come up with this data set and come up with the annotations by asking the authors to annotate these attributes. So I have nothing in particular against feature engineering, but I also don't have anything against learning from raw text if you can. I just think that in this problem, so back then when we did the experiments, the generative pre-training models were not as strong, so we didn't have BERT. We could try now to see if just learning features from these types of models would work better. So instead, because we gave it a lot of this extra intuition about like we think these dependency relations might be helpful, it might be easier to do that to establish a baseline for these tasks. And that's also my answer in general for few-shot learning. If you have a particular downstream tasks and you only want to make sure you get a reasonable level of performance in the short term, then by all means combine deep learning with feature engineering. Otherwise, if you're able to learn it from raw text, then all the better.
Thank you.
I actually have a question. What's the disagreement between the author's labeled attributes versus if a reader labeled that?
Yeah, that's a great question. We didn't manage to get access to readers. We got access to the authors, and they could describe their own characters. But it'd be really interesting to study that, I think.
Because maybe they wanted something to come across and it didn't, so that would be interesting to check.
So there was a question in the front. And who will be next? Nobody?
Thank you for your, I have some questions about the Sanya, yes. I'm interested in the data analysis and the digital transfer or digital twin for smart factory. Yes, sir. Would you try to smart factories digital data transfers analysis system? Or second question is, could you try to genetic analysis in healthcare, for example, like CRISPR-Cas9 or the others new drug development part for anti-cancer or anti-tumor? Could you try this? I wanna.
This is for annotation or for simulation?
Yeah. Data simulation part try to in healthcare, for example, genetic analysis part or anti-tumor or new development, new drug development part, and some the smart factoring data distribution part. Yes, three questions. Yes, sir.
Yeah, we haven't tried any simulation for this. We're just working on the simulators we have in-house right now. But we're working on some medical simulations. I think that's very important for the medical domain in general because data is very sparse. But yeah, not for the domains you mentioned. And smart factory, that also seems like it's very domain specific. I don't know exactly what you had in mind there.
Any other question? No. Sure, you close this. Thank you. and then afterwards.
I have a very short question to Professor Jackie Chang and Professor Kyung-Hyun Jo. I think I think the greatest thing of natural language is the ambiguity, because we can exchange a lot of things just from just one word. But however, anyway, we need to measure some kind of algorithms, so that's why we use BLEU or Mateo and other metrics. So my question is, to measure the ambiguity of the natural language, which metric is the best, and which metric is more realistic to human life? Thank you.
Yeah, that's an interesting question. So ambiguity is definitely very pervasive in natural language. It's usually what I open my course in NLP on. I'm not sure. So there are different kinds of ambiguity, right? There's ambiguity which is in the language, but which we expect the listener to be able to resolve. And then that's the kind that we want our automatic systems to also be able to resolve. And then maybe there's ambiguity that is genuinely there, and so that you actually need to ask follow-up questions or something to actually resolve. So I think, yeah, and there's the other thing that makes this question difficult to answer is that there can be ambiguity along so many different dimensions. Like it could be lexical, it could be syntactic, could be some discourse or pragmatic. Yeah, so I think I don't know how to really measure ambiguity. Maybe you can have better ideas.
Well, I mean, like I don't have a better idea, but so the interesting aspect of thinking about the ambiguity is that regardless of whether it's natural language or not, what it means is that we need to build our systems or the models to be able to maintain a set of multiple hypotheses about what is going on, and then be able to carry it over as it observes more and more of the world. And again, we end up with all those latent variable models, and then how we are going to actually learn to learn, because what happens is that often you can, of course, you can do the full posterior inference and then carry it over. However, that tends to be very intractable. So what we need is that we need a very tractable way to carry over multiple hypotheses and then update them on the fly until it's eventually resolved. And then how we can build a model to do so seems to be a very interesting question that may require some kind of learning to learn or the meta-learning type of the algorithm that allows us to update our own memory on the fly. So my answer is somehow today, my answer to every question is the latent variable models, yes. And then perhaps a bit of a denoising on top of that in order to gradually denoise our belief about what is happening in the world. And then that's probably how we should build the system to handle the ambiguity, rather than trying to identify what types of ambiguities there are and then trying to build a solution for each one of them separately.
Thank you. So there was a question over there, which might be the last question, unless somebody raised their hand very high.
Okay, so maybe I'm not aware of, but do you think it's possible to develop a GAN-like framework for generating like discrete value data like text? Because most of the GAN work, seems to be only on the generating continuous value data. But I haven't seen such. Maybe I don't know. So I haven't seen such work. So just.
I mean, lots of people are trying.
So essentially, every single student I have worked with all wanted to do that, but every single one of them has failed. And then I think the reason is that the amazing strength or the amazing properties of the GAN is the fact that we have an access to the very fine-grained update information and in the input space given by the discriminator. And then that's really well defined in the case of the continuous variables, but when it's discrete variables, especially in a very high dimensional space, without us knowing any kind of compositional structures on that, we really don't have that information other than trying a lot of, let's say, different values. So I'm pretty pessimistic about that approach. I think the right way to go for is to first lift it into the continuous representation space and then do the GAN-like thing in that space.
I agree.
Way to go. So Joshua agrees. Is there any last question? In the back, courageous person.
That's the very last.
For the 27 seconds remaining. Now it's 22. Sorry, it's up. No, just kidding.
So I guess now I have 10 seconds. Okay. So I just have a general question. So one of the topics that interests me is dealing with the shift of the data generating distribution. And I'm still a learner in the machine learning field. So I just have this curiosity, but I don't know how much work has been done regarding dealing with the shift of the data generating distribution. So one thing came to my mind recently is that, for example, fraud detection problem where your decision that you make as, so suppose you're a company that you want to do a better fraud detection. So say you learn, for example, what kind of users are more likely to be fraud. So let's say you make a decision to filter them out. So you let these kind of people not come to the system. And I imagine that kind of decision will affect your future data stream, and it will affect what kind of data you have to train your model in different way for different, say, business or operational purposes in the future. So my question will be generally, if you have been interested in the application of dealing with such shifted data generating distribution, especially when it is originated by learners' decision. So I guess I can say it is kind of about endogeneity of the shift of the data generating distribution.
So Joshua?
So I
-5
won't go
seconds.
into a very long discussion, but there's one keyword you should look for, meta-learning, which in principle is a principled way to deal with out-of-distribution generalization by considering it as an end-to-end problem where you're going to need data that shows changes in distribution, and you need enough of these shifts in distribution to train a system to, for example, quickly adapt to the modified distribution. And so right now, you have to provide those changes in distribution, but there are also people who are looking for extracting those changes from the raw stream of observations.
So that will conclude our panel. Many thanks for your questions, and thanks for all our panelists for this wonderful day of lectures and discussion.
Thank you.